Okay, so welcome to this course on conformal field theory. I'm going to be asking you to submit exercises roughly once every 2 weeks. So please start reading the notes as soon as you get them. So you've got the first set of notes. I'll be sending more notes through as I write them. To examine you in this course, I'm going to be giving you a take-home exam. So it'll be a set of exercises that I think should be quite challenging to you, but you can answer them using, well, whatever you want. So you can consult any textbooks, you can consult me. The only goal is to answer the problems and to really convince me that you have understood the material in the course. And if you have any questions, please let me know. And well, just send me an email or a WeChat and we can discuss it. Good. Okay, so what are we going to be doing in this course? Well, we'll study conformal field theory. So what is conformal field theory? Well, it's usual quantum field theory, except you have some extra symmetry. So in usual quantum field theory, we have Poincare invariance and translational invariance. And we'll be assuming that our theories are Poincare invariant and translation invariant, but we'll actually extend that to the full conformal group. So Poincare transformations and translations are examples of conformal transformations, but the full set of conformal transformations is bigger than this. So I'll have to define for you what a conformal transformation is, and then we'll spend some time working out what is the complete set of conformal transformations. What we would like to know is, if you want a theory to be conformally invariant, what restrictions does this impose on the laws of the theory? So what sort of Lagrangians could you have? We also want to know, how are the observables constrained by conformal symmetry? So for example, if you are to calculate correlation functions, does conformal symmetry restrict those correlation functions? And we'll see, yes, it does. It determines those correlation functions up to a few numbers, at least for 2 and 3-point functions. So that's going to be the goal. These are the kinds of questions that we want to answer. So one question that you might be asking yourself before we get started is, why should we study conformal field theory? So let's talk about that a little bit, and I guess there's a few bits to this answer. So first of all, one reason why we want to study conformal field theories is that they're examples of quantum field theories that have extra symmetry. So why should we care when a problem of extra symmetry? Well, I hope this is a theme that you've detected already in your studies so far. So think about, say, electromagnetism. When you were studying electromagnetism, say electrostatics, you would probably have started off by studying the electric field from a point charge or from an infinite line charge or maybe from an infinitely charged sheet. Why did you study these specific examples? Well, because they were examples that had symmetry. So for a point charge, you've got rotational invariance. For a line charge, you can perform rotations about the axis defined by the line charge. And for a homogeneous sheet, well, you can translate parallel to the sheet. You can rotate the plane that the sheet is in. These are all symmetries. And because of those symmetries, it made the problem easier. And you were able to solve for the electric field exactly. That's not the case for a general charge configuration. So you started off looking at very symmetric situations so that you could actually solve those situations. So in conformal field theory, the idea is the same. We have extra symmetry. And so we expect that these kinds of theories are still going to be simpler than just general theories. What's nice is they don't become too simple. So what I mean is they're not trivial. You really can have conformal field theories that are interacting, but they're still simpler than the generic quantum field theory that you might want to consider. And there are many statements that you can write down, actually motivated by conformal symmetry. So they're consequences of conformal symmetry that are exact statements. I'm thinking here about things like, say, the conformal bootstrap, where you write down an exact equation that must be satisfied by the correlation functions in the theory, and you manage to get a lot of mileage out of that. Another thing that's interesting is that these are the first examples of theories that can be defined without writing down a Lagrangian. So if you think about what we've done in quantum field theory so far, well, you start off with the free theory, and that you know how to solve exactly, and then you perturb the free theory slightly by adding some interactions, but you always assume that the interaction strengths are small. So we're always restricting ourselves to, say, to the weak coupling limit of the theory. In conformal field theory, actually, you can make progress without even knowing a Lagrangian. Just the constraints from conformal symmetry itself is enough for you to start making some statements, interesting statements. And in fact, we know that there are some theories for which you cannot write down a Lagrangian, but you can still study them as conformal field theories. So we want to develop those ideas in some detail. In fact, there is a hope for the field. It hasn't been realized, but this is one of the goals of the field, maybe a very ambitious goal. But the idea is, can we classify all possible conformal field theories? So you might know, for example, we can classify all semi-simple Lie groups. Well, can we classify all conformal field theories? There are people who are actively trying to pursue that. So that gives you some examples of why, conformal field theories are interesting. So in this first chapter, I just want to talk about what conformal symmetry is. I want to talk about some simple examples of conformal transformations. I want to give you some examples of conformal field theories and explain why they are relevant to describe nature. And we'll see conformal field theory plays a role for describing phase transitions, or what are known as continuous phase transitions. Conformal field theories are also relevant to describe the extreme UV, or so the extreme high energy limits of a quantum field theory, or the extreme low energy or infrared limits of quantum field theory. And we'll discuss that in detail too. Now, in this first chapter, I'm going to try to give you some ideas. We're not going to be developing things in complete detail or very rigorously, but I want to give you the ideas and to motivate it so that you have some flavor of the subject, some culture of conformal field theory, and then we'll start to develop things very systematically. So this first chapter is to really give you some ideas. So let's first of all start off and try to answer the question, what is a conformal transformation? So what is a conformal transformation? Well, you've heard me saying that Lorentz boosts and translations and rotations are all examples of conformal transformations, but it goes beyond that. In fact, scalings, where we scale things up and scale things down, that's also an example of a conformal transformation. And there's something else called a special conformal transformation. Well, what the idea is, a conformal transformation is, it's a coordinate transformation. It's a coordinate transformation. And I'm going to tell you what it preserves. So it's a conformal transformation that preserves angles between two lines. Okay? So you could imagine I have a line over here. I have a second line. There's an angle between these two lines, theta. If I do some coordinate transformation, these lines might move around a bit, but I'm going to restrict myself to transformations that preserve the angle between the two lines. It might magnify these two lines or shrink these two lines, so it doesn't have to preserve sizes, but it does have to preserve angles. Okay, we will continue in a minute.